Okay, so for last week, first thing is continue the conducted plateau experiment. So we tried several devices with this kind of structure. The idea is try to compare the source current in straight wire and the source current in those curved wires. Um, and for these three devices, the only one shows conducting plateau is 1014, which I plot data here. So at zero field, there's a peak thing at 4 square edge and 8 square of edge. And at higher fields, we can see very clear plateau at 1, 2, 3 square of edge, and maybe something at 5. But 4 is also missing. I don't know why here. And for 17 and 19, there are no plateau at a zero field, and some wiggling at 1, 2, maybe 3 square of edge. It's on the one node. And for comparing the source current path, you can see configuration 1, 2, 3. So this one source current in straight wire, and this one source current in curved wire. And at 9 Tesla data, we can compare configuration 1, 2, and 3. Basically, there's only some offset, cyclic offset for -9 and 9 Tesla, because I measure at 9. I measure at the -9 Tesla first, then be back to 9 Tesla and measure configuration 2 and 3, which is these two curves. So basically, the plateau position are same for both for three configurations, and they look very similar. So I think the current path would affect the conductor plateau we see here. And the next thing is I finished the manuscript already, and but here I think we only have the structure here, and we need more details, because we need the explanation, maybe the origin of the um, um, single electron pair, which caused the missing of 4 square edge. And so during the manuscript writing, I did some simulation of those conductance plateau data. So this is the first one we have. So we have 2, 6, 8 square edge, but only missing 4. So I made a simulation here. So green line is a single electron conduct plateau at 2 and 4, and for pairs we have 4, 8 with some parameter, and add them together, we can get this red line, which makes the data very well below maybe 10 square edge. I don't know why here. Above 10 square feet, it doesn't fit very well. And another thing is the origin of those conductance plateau. In the manuscript, I focus on the quantum point contact. So I also did some simulation about the origin of those quantum point contact. Because our tip radius is around 7 nanometer, and we do a 5 nanometer erasing. So here I create a Gaussian peak, and the width is around 40 nanometer. Separation is 15 nanometer, which is exactly the same as we create for our device. And when we add these two peaks together, we can have a relatively flat barrier, which I think is the origin of our quantum point contact. And then I think probably we can try some more experiments for multi barriers, because for that we can create a larger flat barrier, which maybe we'll see more clear conductance plateaus. Because for recent devices, we don't see very clear plateaus. Only at a high field, we can see several plateaus, and at a low field, we don't see any plateaus. So I think probably we can try 3, 5 barriers in the future. Maybe we'll see more clear data. I think that's it.